that homework set. Okay, so we had some special cases for lumped capacitance, and I think they are kind of unique because I'm so used to teaching the undergraduate version of this course, and all we do is the convection only case where we have uniform heat transfer coefficient or constant heat transfer coefficient, and that's the case we learned to do. But there actually are a couple other cases that have analytical solutions. Okay, so and they're covered in your book, and they're numbered just like I have numbered them. Special case 3, and this is a general situation. So lump capacitance has to be valid. We may have volumetric heat generation, may have heat flux applied on the surface, and we have convection on the surface. The thing that we can't handle in this fairly general case is that we have to ignore radiation. So the energy balance equation, and the other day we had this general equation. It's up here. All right, so this is our general equation, and I'm just going to rewrite it. And the term that we are going to be leaving out is that we can't handle having radiation. And just another note again, they're using these subscripts to say that the surface area over which I have heat flux being applied in convection don't have to be the same. They can be the same. Okay. By careful selection of some variables, some parameters. So let theta equal t minus t infinity. We've done that one for a bit. And then A is going to be heat transfer coefficient in the surface over which we have convection occurring, divided by rho volume C sub P. And B is heat flux in the area over which that heat flux is applied, plus if I have heat generation occurring within this system. If you look in the book, they show how this solution is developed, and it's not too tricky. I would say the biggest thing is I think you had to have a little bit of insight to think about setting up these parameters A and B to be able to come up with this solution. All right, this isn't super exciting because you guys would know how to apply this, but we're going to look at this problem that applies this solution. It's a long wire, and it's got a diameter of 1 millimeter. It's submerged in an oil bath. So this really long, skinny wire. Oil bath, and the oil bath has free stream temperature of 25 degrees. the wire has an electrical resistance of, and that prime there is same per unit length, so 0.01 ohms per unit meter, and a current of 100 amps flows through the wire. A convection coefficient of 500 watts per meter squared Kelvin acts on the wire. And what is the steady state temperature of the wire? So that's not so exciting. We've been doing steady state for a while. The interesting part comes in part B, where it says from the time the wire is put into the bath, so at its initial temperature, how long does it take for the wire to heat up to within 1 degree of its steady state temperature? All right. Okay. This section is a lumped capacitance section, so likely that we're going to need to check, but that will apply a lumped capacitance solution. And I'm going to list that we're assuming constant properties. We just talked about this special case that has no radiation. And just to talk about this for a minute, if we're in air, if we had this wire in air, listing that we're neglecting radiation is maybe a little bit more important because we think of air as nearly transparent to radiation, to thermal radiation. But if we have this wire in water, we have it in oil, there is not, we don't consider the radiation effects because we don't have radiation traveling through that fluid to a solid surface. So I'm not going to list no radiation because they told us we're in this wire bath. We wouldn't expect to have radiation. Okay, I do need to tell you the properties for this wire. Well, and really I had it up here with constant properties, but I already had started this. So KW wire is 220 watts per meter Kelvin, CP 500 joules per kilogram K, and density for lumped capacitance to be valid.
I have a quick question.
Yes.
For those properties, those would be given, right? That wouldn't be something we would have to look up based on the resistance or anything?
If I wrote a problem and I gave you information on properties, yeah, I hope that you have a source for looking up properties.
Okay.
But yeah, this one hasn't given enough information, so so I'm listing them.
Okay, thank you.
Sure. Okay, so we want a small PO number. We talked about how we calculate the characteristic length. Okay, and this is a really long wire, so we're neglecting, it says it there. We're neglecting end effects. So I come up with diameter over 4 if I plug in numbers for volume and surface area. Yeah, wire is 1 millimeter. So 1 times 10 to it is the diameter. 1 millimeter. And okay, So 2 zeros and 6 3. So this behaves as a lumped capacitance system. Other ways to say it would be zero-dimensional transient or space-wise isothermal. So we started out down that path, but first part really is to solve for steady state temperature. In our problem, they told us that we've got a current and we know the resistance. So we've got generation going on, heat generation going on inside this wire, and then that's being convected away from the wire in that oil bath to keep us at a steady state situation, at least in this first part. And just rearranging the equation. Okay, the power generated or dissipated in that wire is going to be R squared I, or no, R I squared, sorry about that. So the thermal resistance times the current squared. But since they gave me per unit length for this wire, I'm adding a length. We don't know that, but I've added it in. And then we'll expand this out one more time. So the surface area is pi dl. Okay. And now I want to rearrange this equation. Yeah, I'm trying to solve for T. Okay. Boy, I don't do electrical engineering type calculations very often, but just to remind you that an ohm times an amp squared is going to give me a watt. Unit wise. All right, so just thinking through. So we got a watt per meter, and then, oh yeah, watt per meter squared here, but we got another meter all right over here. So we end up with units of temperature. I am very used to writing for convection that off the surface. So we think of that as the surface temperature of this wire. But we've already said that this wire behaves as a lump capacitance system. So really, the temperature is nearly uniform at this 88.7 degrees C. So throughout the wire. We looked at what the solution to this equation looks like already. So I think that's a handy place to start. You know, I did some development. Again, I want to remind you, we're ignoring radiation. Okay, so we're looking for that particular solution. And it looks like all right, and this does not look quite like what I had written down earlier. So now I got a little bit of a question, but this is equation 5.25. Okay, and I'm thinking it's a rearranged version. I had a rearranged version earlier. Okay. So I'm scrolling back up for a minute. I need to be reminded. So we initially started at a temperature of 25 degrees C. We got an oil bath temperature of 25 degrees C. And we want we want to figure out the time. So we're looking for time for this to get within 1 degree of 88.7. Where is it? Okay, 88.7. So we want this to get to 87.7 degrees C. So if I'm looking at this part of the equation, we know what this final temperature is. We know what the temperature of the bath is. We know initial temperature, T infinity. And we got a little problem there, but let's look at this for a minute longer. We said that it's a combination of things like rho, heat transfer coefficient, some surface areas. Okay, and here's our unknown time. B, we looked at that, and it's a combination of volumetric heat generation and I think a heat flux. Okay, but some things we should know. Okay, and then we got this unknown T lurking over here also. So this this is not an easy to solve, but it looks like we have a single unknown in it. So that's our goal, is we want to solve for temperature, or solve for time. Okay. All right. We just looked at this, and this said that Ti, the initial temperature of the wire, is 25 degrees C, and T infinity is 25. So we got this divide by zero issue. So the plan is, let's multiply through by Ti minus T infinity. Okay, and we've got Ti minus T infinity already here, so this simplifies this one a little bit. And then, since this is equal to 0, we end up dropping this first term that has the just the exponent, not the 1 minus exponent. So our equation looks like I did a side calculation to come up with the values for A and B, rather than substituting all of those things in. And at the slide we looked at, we're using these definitions for A and B. And for our particular problem, oh yeah, we had no heat flux, so that Q double prime term is gone. You know, this looks like a whole lot like the reciprocal of time constant that we saw the other day. And I went ahead and substituted numbers in at this stage. The surface area that convection occurs is going to be pi times diameter. And length, ooh, I'm just leaving length as a variable. Density for the wires given, volume, pi over 4, diameter squared. And then we got a length, and we're feeling good because we got rid of those two lengths. And specific heat. Ooh, 500 joules per kilogram. Okay. Does anybody remember what the units for time constant are?
Probably seconds to the -1.
Seconds. I think we had before it was T over tau. And so we know that, well, we can put any time unit in, but if we think of this as in seconds, then the time constant should also be seconds. So you are correct. This A is really the flip of time constant. So I would expect we get units of 1/2. I shouldn't go through all this detail, but I like that you think through. And I can already see I got this unit of watt, and it's a joule per second. And all of my other units should cancel out, and I end up with 0.5, and it's 1/2. Heat flux, that's gone. But we've got heat generation going on through this wire, and it's the R prime and I'll put the L in here again, and 100 amps squared, and rho and again, this combination of terms gives me watts, and I got joules on the bottom. And B gives me units of Kelvin per second.
I'm sorry, did your units just line up the same though?
Say that again.
They're both joules per watt second. So how is the Kelvin over seconds?
Ooh, why am I getting this thing on the screen? Go away. Okay. Why are the units different?
Yeah, because you wrote joules over watt second for both, but then the units at the end are A is 1/2 and B is Kelvin over seconds.
Yeah. Okay. Oh, whoa. Okay. All right. So here I had it. So I'm looking at A. I got a Kelvin up here, and I got a Kelvin down here. So I got rid of my Kelvin. Is that where your question is?
No, I think it's just I saw joules per watt seconds in the second for B, so it should be joules Kelvin per watt second. Or is that not the case?
Oh, no. All I was trying to show is, so if I think through, I'm canceling out units. So this guy gave me watts. Okay. So I know I want to get rid of watts. And I got joules down here. I get rid of that. You still have to go through the other units. And I got this Kelvin down here. But you made me think about this for a minute. So I got a Kelvin down here I don't get rid of. So I got to keep it. I had a Kelvin here and a Kelvin there. All I wanted to show with this is how I get from watts and joules per second. That gives me this time unit. It happens in both of these.
Okay.
Okay. So I keep looking at why I did something a little bit different. Okay, but okay. So I'm back to this equation up here, T minus T infinity. So we said we were going to be at 87.7 degrees C minus 25. Let's see, I had B over A, so B is Kelvin per second, and A and 1 minus exponent minus 0.50, 1 over second. And then I need a time in here. If I work back and solve for time, it's pretty fast, 8.4 seconds for the wire to be plunged into that bath. Actually, it could be sitting in the bath because they're both at free stream, but I suddenly start heating it up. I suddenly start putting that current through it. And it should get very close to its steady state temperature. Okay, so that was an example of using that solution. We had this, I think this is kind of unusual that we had the divide by zero problem. I'll try and find another one for you to test this equation out. It feels pretty all-purpose. Besides ignoring radiation, we can do lots of other things with this solution. Okay. Before we move on to lecture 11, I said I wanted to chat for a minute. I normally have you this short presentation on convection. So I give you a problem, and it's something a little bit different than just I shouldn't say different, but let's see. For example, one of the problems I like to give is an unheated starting convection problem. So the fluid problem is building up, but the heat transfer problem isn't building up. And we haven't talked about convection. I know some of you, this may be fresh in your mind, but just an example, that's something you cover typically as an undergraduate. So it's something that I thought we would cover. The idea is I assign some groups. I don't know our exact numbers. I think we're not quite at that point where we have 3 per team, but we're close to 3 on any team. So my question is, if you had at least a week to do this, and prepare a PowerPoint presentation, and then you would give it to the class, does this just work out okay? Are people comfortable enough and collaborate that you can take the screen over and you group of 2 or 3 would be able to give a presentation? They're probably 10 minutes. They're not super long.
I think from a technical standpoint, I would have no problem with that, but I'd be interested in seeing what the specifics of the assignment are, like the handout says.
Oh, okay. Because, I mean, well, so if you're saying the technical aspect, that's what I care about. I won't leave you hanging about giving you maybe takes you a little bit of like looking in the book and figuring a few things out and talking it over with your partner. But I think technically, the content I think you will be okay with. If you think that preparing something and you are able to work with each other, okay. Let's talk. So, okay, does anybody else want to chime in? I'm assuming you guys do this in work all the time. If you guys are not working, you're not physically going to your buildings.
Just curious, sorry, when's it going to be due?
I don't know precisely, but it's coming out. So, like within the next, you'll have your exam November 1st, but it might be, I don't know, pretty soon after, like maybe the next Monday.
Okay, yeah, I'm personally happy it's right after the exam, so.
Okay, so let me think. What is my next question? Okay, maybe I don't have another question. All right, so convection, let's do some really detailed things. I kind of like doing these, you guys explain the problem to me and for that. But I would like to do maybe one day of, general discussion of convection, just to jog your memories, and then get these problems out to you pretty quickly. Oh, I do know what I want to ask. I often assign groups, but I don't know if there are particular constraints. So let me think through groups of 3 likely, and then maybe it's going to be a couple groups of 2, and then maybe I'll let you give me your preferences, and hopefully there are enough of you who won't have your preferences that I can fill out teams in a reasonable fashion. But I may get teams put together even before we get problems assigned. So my goal in this is I don't mean for it to be a huge heartache for you to work together, that, I don't know, somebody's working really weird hours and you never can catch them. But I also realize I'm not necessarily going to be able to put all of the teams together quite as you request. But okay, I'm going to write you an email. We'll get started on this. As a syllabus, this is one of the things. I have some title for it. I don't know, it's a special problem or something. This is going to be one of them. There are some points associated with that. This is starting lecture 11, and I only posted this maybe 30 minutes before class, so hopefully people have a chance to, that you can access it. This is still lumped capacitance. So again, we have to think about this object. We can have the temperature changing with time, but it's a uniform value throughout the material. This is a case with convection only. So, back to, previously we had case 1 was convection only, but H was constant, and now we can allow H to vary. Okay, but it only varies as, so the temperature of the object minus the free stream temperature. But if you think back of your previous knowledge of natural convection, that's that is what the heat transfer coefficient is. We end up basing it on a Grashof number and Grashof-Rayleigh, and it's driven by the temperature difference between the object and the free stream. So to me, this one is just calling out. It's saying, when I have free convection, this could be a good option for how to develop a solution. Here's the form for the heat transfer coefficient. So I'm going to say it's a function of T minus T infinity, this temperature difference. And then we have some constant and some exponent, and it varies. Okay. And as I was looking over notes, I want to be clear that that is a C constant. It is not heat capacity. Okay? Because we end up having heat capacity up here in these equations, and I'll try and be careful and make sure I keep putting up T as a subscript so you know they're different. Okay. So I'm going to this next slide. This is taken from the book by Holman, which is a reasonably popular book for an undergraduate heat transfer book. And this is simplified equations for free convection for various surfaces to air at atmospheric pressure. And if we look at this, so this is saying a vertical plane or cylinder, and they give the heat transfer coefficient. And it's got a delta T in there, and delta T is, I don't know what that W in precisely, but that's the surface minus T infinity. So that's just what we showed in that previous slide. It's got a heat transfer coefficient, and it's written as some constant, some exponent n, and then we've got a characteristic length to worry about too, but it's got the delta T. Okay. So my only reason for showing you this is that you're believing this idea that it is possible to write a free convection heat transfer coefficient in terms of some constants and an exponent, and then this temperature difference. Right. This is not the way Increpera and DeWitt, and it's now Bergman and Levine, not the way our book does things. They don't show this. But so it was a little bit new the first time I took a look at this, but I think it's kind of interesting. Again, it holds for just a very particular case of air at atmospheric pressure, but we see that case pretty often. And it also brings out this idea that for laminar flow, this exponent is different. Okay, so back to this case. So imagine we have some object, and we're going to say that we have convection leaving. We have no volumetric heat generation, but it's a transient problem. So we've got to keep the storage term. And if convection looks like okay, but now we're replacing H. Just to make it look a little bit more simplified, and we're going to combine these guys apologize, this is kind of important. Remember, our heat transfer coefficient had this exponent n. So I should have T minus T infinity, and then at the end of the parentheses, I should have the exponent. All right, so we're going to separate variables. Oh. And separate and integrate, and the solution ends up looking. And this is not trivial to get from this step to the next step. All right, and so I don't know, this is not very physically satisfying to look at that equation, I don't think, but you know, I can follow the development of this differential equation up to here. And then we got to do some rearrangement to get to this last form. So this is a problem to work with a free convection heat transfer coefficient given, and they gave us what to use for C, and they gave us what to use for N. And I kind of like this because we saw up here that we had a lot of times where N was equal to a quarter. Okay, so this looks like a pretty reasonable. Do we have anything with 2.8? No, we don't have any coefficients that high, but the exponent looks reasonable. Okay, so a long, highly polished aluminum rod is hung horizontally in a large room. The initial rod temperature is 90 degrees C and the room air is 20 degrees C. The free convection coefficient is modeled as, and assuming that free convection is dominant in the room, calculate the time for the rod to cool to 65 degrees C. So one, assume the cylinder is long enough to model as an infinite cylinder. That's the thing I keep forgetting to add in here. But again, we're just saying we got this long cylinder and we are neglecting heat transfer off of these little ends. We only consider heat loss off the cylindrical surface. And we're going to assume that lump capacitance is valid, and we'll check that eventually. And okay, we're going to assume properties for aluminum. And these are going to be constant properties. And again, so we're going to try and solve for time. So if I look back in this equation that we're going to implement, yeah, we're going to end up solving for this guy. So a little bit of rearrangement to the equation. Okay. Oh, I know what, I keep doing this. Let's see. We're going to start by seeing if lumped capacitance is valid. And ultimately, we aren't always going to have lumped capacitance because we're heading in this, maybe one more problem we're heading towards where lumped capacitance is not valid. All right. So I'm going to do the two extremes. Let's see. The initial rod temperature is 90 degrees C. And we want to get it to a final temperature of 65 degrees C. So we would expect that the initial temperature is going to give us a bigger temperature difference, and it's going to give me the higher convective heat transfer coefficient, and it's going to be the more critical case to check for lumped capacitance. But we'll check them both. All right, so our C is 2.8. Okay, I'm not going to watch units very carefully. You see these wacky units for C. It's because when I take my temperature difference, it's raised to the 1/4. So our K down here is 1.25. But we're going to get back to our normal units of H of watts per meter squared Kelvin. Okay, so initially we're at 90 minus 20. And N is 0.25. Okay. These are really small differences, but and if you remember back, free convection, the heat transfer coefficients are small. We're in air, it's small. So this is a pretty tiny difference. But let's go ahead and use the more restrictive case. Okay, so we are doing an aluminum rod again. So it's diameter over 4 that I would use for characteristic length. All right, and my diameter was 35 millimeters. Wow, so 3 zeros and a 3. All right, so we're not in danger of not meeting our lump capacitance requirement. I'm just rewriting this equation again. T plus 1. And doing, and minus 1 over n. First rearrangement I want to make is I'm going to take this exponent to the other side, and I'm also going to remind myself that theta is t minus t infinity, and theta I is ti minus t infinity. Okay, and then I want to take the minus 1 to the other side. I'm just rearranging to get t on one side. Okay, and I'll show number substituted in. So that looks okay. That just gave us a number, no units to worry about. Okay. Rather than having to solve for volume and surface area, because we really did that when we checked whether lump capacitance was valid, I'm going to substitute in characteristic length for that ratio. Okay, so the units for C are a little bit unusual, but then I have this temperature difference. And it's raised to 0.25. So crunching through the numbers, it says that it takes 1,249 seconds. What do? We put this bar to cool down to 65 degrees C. All right. So the first time I thought about this equation and thought, man, this is really going to be useful to have a way to handle free convection. But let me show you one more calculation and see what you think. We had free convection, which is driven by this temperature difference between the object and free stream. Okay, but let's say I'm going to pick an average constant H value. Okay, so we calculated those two H values up above, and it was, one was 8 and one was 7.6. No, one was 8 and 7 point, well, what was it? 8.1 and 7.2. All right. So the average of those two is 7.68. And now let's just assume I do that case 1 of lump capacitance. I have convection only. Okay. We've seen all of these things before. Nothing changes from that earlier case. Again, we have a simpler looking equation. If I plug in my numbers, I get 1,246 seconds. Okay. All right. I have not found a problem yet where using this precise ability to handle free convection heat transfer coefficient has made a big difference. Again, many times these free convection heat transfer coefficients, they're pretty small anyway, so they're not changing a whole lot. So, accounting for their small variation versus doing a good job to get the average doesn't give a big difference. So, like I said, I thought it was really cool when I first kind of saw this, but if you take some care in finding a good you're going to do an okay job with your estimate. So one more thing, though. How do I want to sketch this? All right. If this is lumped capacitance, okay, and we're thinking this is the temperature of my object, and I've just non-dimensionalized it. So That's my object temperature minus T infinity over initial minus T infinity. And for this case that we just did, for example, lump capacitance, we know that we're going to get closer and closer. Eventually, I'm going to get to the object would be at T infinity. So I drop to, I'm getting to 0. So if this is my lump, H equals a constant. When I have this free convection that gives me a higher heat transfer coefficient when my delta T is larger. So when I have initially, put this object to be cooled down, you see, let's see if I can sketch this, that I have a little bit higher. Right. That originally, I did them backwards. So let's do, this is my constant. H. All right. And let me change this guy. Okay. So early on, I have a bigger heat transfer coefficient than my average constant value. So I'm seeing the temperature drop off a little bit faster when I use that a little bit more complicated equation rather than that constant H value. And then there's a period of time where the constant H value is bigger and it's doing it, it's cooling off at a little bit faster rate. Okay. And it depends on, again, because I picked the length of time, or I picked the length of time that I was applying those two heat transfer coefficients. For my case, they end up getting us back to the same point. We cooled it down to 65 degrees. So I have a period where one is higher than the other and one is lower. The next thing, so let me finish this up. So I was saying, when we calculated time, we don't see much difference between these two cases. You might do, I don't know, depending on what you're looking at, you might do a more precise job if you were looking for a particular temperature at a spot and you used the free convection assumption in calculating temperatures. Okay, I'm going to end class for today, and I will wait a bit to see if there are some questions that you want to ask.
Thank you.
Yeah,
Thanks.
you.
Thanks, Dr. Prehab.
Thanks. Have a great weekend.
Oh, it feels like we got more to go, but you're right. For this class, we are done for the week.
Hey, Professor.
Yes?
I just wanted to apologize for turning in my homework when you reminded us about it in class. I had to email it to you because I guess the Blackboard locks it exactly at 4 o'clock.
Okay.
My apologies on that.
Okay. So do you have a minute to hang on? If I like open it up, like if you had 5 minutes, I'll
Yeah.
open it up and you can turn it in?
Yeah, I can do that.
Okay.
Yeah, it was. I tried to submit it, and when you told us, I was like, "Oh shoot, we had to submit that." But yeah, I can do that.
Okay. And I'm away from where the microphone is to get this done, but I'll let you know when I got it.
Okay, sounds good. Yeah, I emailed it to you just because I wanted to make sure you knew it was done. I just needed to submit it.
Okay. And it just makes it easier if they're all in one place when I go to grade. So
Yeah.
that's my reason for.
No, that's 100%. It was on me. I just got caught up in work. So I guess it was supposed to be unlocked.
Say that again.
I said I guess it was supposed to still be unlocked to be able to submit it.
Oh, well, so no, I do want to know who turns it in late in general.
Yeah.
So I do lock it, but it's way easier. I mean, I'm gonna assume you had it done. This was just a glitch, and it's way easier if it's all in one place. So I'm unlocking it till 5:30. You can sign off if you want, if you didn't have any more questions, and then I'm going to assume that works fine for you.
Okay. Let me just go ahead
Oh,
and
See if it's there. Okay.
Yeah.
Yeah.
I might as well do it now. Let's see. Assignments. There we go. I think it's okay. Yeah, I can submit it.
Okay. Cool.
Awesome. Thank you.
Sure.
Have a great afternoon.
Thanks.